we're going to wrap up talking about properties of functions today. So let's start off by letting f of x be some function. We say that any y value, f of x, remember f of x represents the output or the y value. We say a y value is a local maximum for a function if f of x, if the output, is greater than other y values, other outputs in a neighborhood around it. Essentially, what you're looking for is you're looking for the y value of any peak in your graph. So if it looks sort of like a mountain range, any kind of a peak is going to be a local maximum. And analogously, we say that any y value f of x is a local minimum if it's smaller than other y values in some neighborhood around it. So what you're looking for here is something like a valley in your graph. Right? So just by observation, we can see here that there's peaks at this point and at this point. And there's a valley down here. Looks like it's at maybe, it didn't draw this very well. It should be a noticeable valley, so maybe something like this. Okay, so in this case, the valley, the local minimum would be at 0, 1. Okay, now the maximums and minimums themselves are the outputs of the function there. So the output, the y value of this point, right, this point is at -2, 2. The y value is at 2. So we have a local max at 2, right, y equals 2. And then the y value up here, this point looks like it's at about 4, 4. So the y value happens to be equal to the x value, but the y value is 4. So we have another local max at 4. We also happen to have a local min here. The coordinates of this point is 0, 1, and the local minimum is the y value there, so we have a local min at y equals 1. Okay. Now, sometimes those local maxes and mins will also happen to be either the largest output of the entire graph, the largest y value, or the smallest y value. And if that's the case, then we would call that y value a global maximum or a global minimum. Sometimes they call them absolute max or absolute min. That's another word you might see that means the same thing. An absolute max or an absolute min would be the largest output of all outputs in the graph for max, or the smallest of all outputs in the graph. Now, we have a local max at 2 and at 4. 2 is obviously not the largest output of the graph because up here we have an output at 4, right? But there's also outputs here at 3 and 3.5, etc. But this point here, this is the tallest peak on your entire mountain range of a graph, right? Which means 4 is the absolute maximum of the entire graph, or the global maximum of the entire graph. Now, is 1 going to be an absolute minimum? No, there's other smaller outputs. For example, over here we have an output of 0, here we have an output of -2, etc. In fact, you can always get more and more and more, or I should say, larger and larger and larger negative outputs by following this graph down towards negative infinity. Okay, so a couple more properties of functions that we want to talk about. Symmetry. So some graphs have a nice property that they're symmetric in some sort of a way. So I'm going to give you an example of what we call an even function. So an even function is a function that's symmetric around the y-axis. In other words, if you reflected the graph across the y-axis, you just get that same graph back again. So if we look at the function f of x equals x squared, this is symmetric across the y-axis. If you reflected it on the y-axis, you get the exact same graph again. This happens to have the property that f of x is equal to f of negative x. How do we know that? Well, if we were to find f of negative x, that would be negative x squared, which is, well, negative x times negative x is just x squared, right? Positive x squared, which happens to be equal to f of x. So algebraically, we can show why this satisfies this property right here, that f of x is equal to f of negative x for every possible x value. Another way of thinking about it, if you take a number here, x, right, and then you take negative x, you get the same output for both. That's how you have that symmetry on the y-axis. Another example would be something like, I'm going to say the function, let's call it g of x. Give it a different color here. I'm going to take x to the fourth power and I'm going to flip it upside down and shift it up. So negative x to the fourth power plus 1. That looks like this. Okay? It's steeper than a parabola, but it's the same basic shape as a parabola. It's been flipped over the x-axis and then it's been shifted up 1 unit. And we can see that this is symmetric across the y-axis, which means that it's even, but we can also explain why it's even algebraically. In other words, we can show that g of negative x is equal to g of x. So g of negative x is going to be, all right, I'm going to have to replace every instance of x with negative x. That would be negative of negative x to the fourth plus 1. So that's going to be negative of x to the fourth plus 1, which is, again, negative x to the fourth plus 1, which is exactly what g of x is equal to. So this is how we can show algebraically that a function is even. Notice that this x squared function was even. It was a translation, sort of not exactly an x to the fourth on its own, but x to the fourth that's been translated around a little bit is also even. And so it should be no surprise to you that any function of the form, say h of x equals x to the nth power, where the exponent is even, is going to be an even function. Why? Well, we need h of x to be equal to h of negative x. If we plug negative x into this equation, we'll have negative x raised to the nth power. And since n is even, all of those negative signs will cancel each other out and you'll still get x to the n again. That's why we call these even functions, because it's a property that all x to an even power functions have. Now let's contrast that with an odd function. So we define an odd function to be a function which is symmetric around the origin. Okay, what does it mean to be symmetric around the origin? One way to describe that is it's a function where, let me draw a picture first, something like this. So it's a function where if you rotated it 180 degrees centered at the origin, you'd get the same graph back. Another way of saying that is if you reflected it across the x-axis and then the y-axis, you get the same graph back. Okay, so just to show you how that works, reflecting it across the x-axis would give me this. And then reflecting that green dotted line across the y-axis would give me this. Okay, so doing both reflections, you have to do both, gets you the original equation back again. Well, what function is this? This, of course, is the x cubed function. And similarly, if I wanted another odd equation, let's say g of x is, how about negative x to the fifth power. That looks sort of like this one, but it's been reflected across the y-axis and it's steeper, so it's something like this. Okay, this is also going to be an odd function, and just like before, we can prove it algebraically because the way that we define an odd function is a function such that f of negative x is equal to negative f of x for every x in the domain. To see that on this graph, if you picked a particular x value, f of negative x is this value here, and f of x is this value here. Oh my goodness. Here we go. Here's your f of x. And if this is negative x, right, the same spot on the other side of the axis, f of negative x is down here. So we can see that f of negative x is equal to the opposite of f of x. In other words, the point you get up here is sort of reflected in the third quadrant down here. Alright, so algebraically that would look like we need to show that f of negative x is equal to negative f of x. Well, f of negative x here would be negative x cubed, which is negative x times negative x times negative x. So because we have three negatives, overall this is going to be negative, and we have three factors of x, and negative x cubed is indeed equal to negative f of x. the opposite of f of x. So we can see why algebraically this is going to be correct. This gives you an odd function. And just like before, we can generalize and say that for a function of the form f of x equals x to the nth power where n is odd, the function itself is odd. It is an odd function. That's why we call it odd, because it's a property that x to an odd power shares for every odd power. All right, to wrap up our talk on properties of functions, I just want to talk about rate of change of function. We've talked about rate of change already when we talked about linear functions. Remember that for a linear function, the rate of change is constant, right? The rate of change is just the slope of the function, and the slope of the function is always the same, right? It's just whatever that m is, whatever the coefficient on x is, if it's mx plus b. For a nonlinear function, the rate of change is going to depend on which x values you choose, right? If I wanted to look at the average rate of change over, let's say, the interval from 0 to 2, on average, the rate of change of this function is going to be sort of a large number, but if I looked at the average rate of change over the interval from -2 to 0, the rate of change is going to be a negative number. But we can sort of try and get at the idea of rate of change by looking at the average rate of change. Okay, so the way that we find the average rate of change is as follows. To find the average rate of change on the interval from a to b, so those are x values, right? So some interval on the x-axis. We just need to compute f of b minus f of a over b minus a. In other words, find the slope of the line connecting those 2 points on the curve when x is equal to a and when x is equal to b. Let me give you an example. Let's look at this function here, and we'll find the average rate of change. I'm just abbreviating this as AROC on the interval from 0 to 2. To do that, I need to compute f of 2 minus f of 0 divided by 2 minus 0. All right, well, let's go up here for a second. F of 2 would be 2 squared plus 2. That's 4 plus 2, which is 6. And f of 0 would be 0 squared plus 2, which is 2. So this average rate of change would be 6 minus 2 on top over 2 minus 0. That is 4 divided by 2. Or just plain 2. Notice what we were really finding there is we were finding the slope of the line that connects those 2 points on the curve. The point at 0, 2 and at 2, 6. So the slope of that line would tell you the average rate of change of f over that interval. This is going to become very important when you hit calculus, right? But really all you're doing is finding the slope of a line connecting 2 points. If you have a line connecting 2 points on a function, we call that a secant line, by the way. So the average rate of change is really telling you the slope of a secant line.